So let's look at the solution to this precipitation practice problem. It involves following the fate of an air mass as it arrives from the Pacific Ocean. This here is supposed to be a cross section over there. That's my little tree to indicate that it's a cross section. So an air mass comes in from the Pacific Ocean at near sea level here, and then it's going to be deflected up and over a mountain. So as it is deflected up, we know that it's going to cool. Rising air masses are cooling air masses, and eventually it will become, at point B, a precipitating air mass. In other words, we're going to start forming rain at B. And then from B to the summit, it's going to continue rising, right? I'm going to give it a different color to indicate that it is now precipitating moisture, right? It's going to reach the summit, and then on the way down, it's going to go all the way down to point D, which is no longer, it's not at sea level, it's above sea level, but it's on the way down. Okay, so we want to follow the path of this. We want to trace the fate of this air mass in terms of its temperature and its moisture content as it goes from A to B to C to D. The incoming air mass, we're told, has a specific humidity of 13 grams per kilogram and a temperature of 26 degrees. So it plots right here at the black dot. And as it initially, so this is where it is at A. And as it comes in then, it's going to be deflected up the mountain. And as it rises, it cools. So along this path that's shown in the light blue from A to B, it's going to cool. On this diagram, that cooling process is going to be shown as a horizontal line to the left like this. Okay, so here it is. It's constant. It's not changing its specific humidity. The only thing changing is its temperature. And it's going to continue on this path, on this diagram, until it reaches this saturation curve right here. We'll call that point B. So when it reaches this point now, it's on the saturation curve. And as it rises even a foot higher, it's going to begin forming water droplets, which we're assuming are going to form precipitation. So the first part of the journey takes us from A to B, and we have to figure out the elevation at which this happens. So what do we know? We know that it comes in at sea level. That's 0 meters above sea level. We know that the summit is at 1225 meters, and that the other side, D, the final destination, is at 275 meters. But we don't know the elevation at which precipitation begins. But from the diagram, we can read off the temperature change that must have occurred to get there. So if we read carefully here, point B is at 18 degrees C. Point A was at 26 degrees C. So this temperature change that occurred as it rose up the mountain was 8 degrees C. And because we're rising without precipitating, we're going to use the dry adiabatic lapse rate of 10 degrees C per kilometer, which is the same as 1 degree C per 100 meters. And I can do this in my head. If it's decreasing by 8 degrees and it takes 100 meters to do it, then to get 8 degrees of a decrease in temperature, we have to rise 800 meters. So we know that point B here happens at 800 meters. So at that point, we've reached point B. Now, the next part of our journey is indicated by the darker blue line, and that is the journey from point B to the summit. We know that during this time, precipitation is continuously forming. So from this part of it, the journey, we're going to be using the moist adiabatic lapse rate to describe the additional cooling, and that is 6 degrees C per kilometer, or 0.006 degrees C per meter. It's going to turn out that this is going to be an easier number to use. So to reach that, what do we know? Well, we know the elevation of 800. We know the elevation at the summit. So the total elevation gain is going to be 1225 minus 800. That's 425 meters. 425 meters of additional ascent, during which the temperature is decreasing by 0.06 degrees per meter. And when we multiply those two together, 425 times 0.006 degrees C per meter, that turns out to be an additional temperature loss of 2.5 degrees C. So along that part of the journey then, we're going to draw that with that dark blue line. Water is following this curve, and it's going to decrease by another 2.5 degrees. Is that right? So it's going to go from 18 degrees down to 15.5 degrees, if I do this right. Is that right? Did I do that right? Okay. So right here, again, what we know now is it's decreased by 2.5 degrees. So we were at 18 and now we're at 15.5 degrees. This is now known, this 2.5 degrees. We learned that from the fact that it had to rise 425 meters to reach the summit at the moist adiabatic lapse rate. That corresponds to a further decrease in temperature of 2.5 degrees, bringing our temperature at the summit to 15.5 degrees. So there we are. It's right there on our line. At this point, the relative humidity, we should know we're on the line. Anytime we're on the line, the relative humidity is 100%. The specific humidity, we follow the line down, is now at, looks like about 11, right? So when we reach the summit, we're at 11 grams per kilogram. What happened to the 2 grams per kilogram that we lost? Well, that was converted into water droplets, right? It's precipitated. After we reach the summit at point C, we are now going to descend all the way to point D. And as we descend, the temperature is going to warm up. So we were at point C here. I'll give it orange there. And we are going to descend. And as we descend, the temperature is going to increase, which means we are going to move off of this line in a direction like this. Temperature increasing. Our specific humidity is going to stay the same. We're not causing any of it to come out of solution as water droplets. So we're using now, once again, the dry adiabatic lapse rate, and we are going to descend a distance. Well, we know what that is. We can calculate that distance. This is 950 meters. And we're going to descend 950 meters at a rate of 1 degree C per 100 meters. You can maybe do that in your head. That turns out to be an increase in temperature, right? We're descending of 9.5 degrees. So we were at 15.5 degrees, right? We're at 15.5 degrees. We add 9.5. That brings us exactly to 25 degrees. So this path to go all the way out here to 25 degrees right there. And our final destination, we reach it at a temperature of 25 degrees. We're at D now, 25 degrees, and a specific humidity of 11 grams per kilogram of air. So let's just write this down. At D, we have a temperature is 25 degrees C, and the specific humidity Q is equal to 11 grams per kilogram of air. We are also asked to calculate the relative humidity here. That's easy. All we need to do is take our temperature. We're now at 25 degrees C. We need to know, remember, the relative humidity is equal to the specific humidity divided by the specific humidity at saturation. We have to read that off the graph. So 25, well, what do you know? It makes it nice and easy. So the saturation value here, QS at 25 degrees, is equal to 20, right? So the relative humidity will equal 11 grams divided by 20 grams per kilogram, 11 grams per kilogram divided by 20 grams per kilogram, and that is 0.55 or 55%. All right, now 2 other things. Oh, I forgot one other thing we were supposed to do at the very beginning, and this is a relative humidity thing again. So at the very beginning, we were supposed to calculate the relative humidity. That's doing it exactly the same way I just described, except now at the beginning we're at a temperature of 26 degrees. So our relative humidity will be the value at A, which was 13, the value of specific humidity, divided by the saturation level at 26 degrees, and that looks like it's more like 21 grams per kilogram. That turns out to be about 0.62 or 62% relative humidity. So our relative humidity started out at 62% and it ends up at 55%. We're also asked to express the water vapor concentration in the air in terms of partial pressure, and we're going to do that through the relative humidity. So we'll go to the other, remember the first one, this was at 26 degrees C, 62%. I'll write that. That's at the beginning at A, and at the end we were at 25 degrees C and 55%. This was at point D. So let's convert those into partial pressures on the partial pressure diagram. So initially we were at 26 degrees C, and what we need to do is we're going to use exactly the same idea. So the relative humidity is equal to, now on this diagram, it's equal to the actual water vapor pressure, partial pressure, divided by the saturation level of water vapor. So at 26 degrees, saturation here looks like it's about 2,700 more or less, 2,700 pascals. So the relative humidity is equal to the actual humidity partial pressure divided by the saturation partial pressure. If I could just sort of rearrange this equation, the partial pressure is equal to the saturation level times the relative humidity. Well, saturation level in terms of partial pressure is 2,700. This is point A, where we started, times the relative humidity of 62%, 0.62, and that turns out to be about 1,700 or so pascals. So that's our partial pressure at the beginning. At the end, at D, remember we had a temperature of 25 degrees C and a relative humidity of 55%. We're going to use the same idea, so we'll give that a different color here. So at the end, at D, our temperature is at 25, and our saturation level now looks like it's 2,600. So E saturation is equal to 2,600 pascals. And our value of the vapor pressure, the water vapor pressure, is going to be equal to the value at saturation times the relative humidity of 55%, 0.55. And that is going to turn out to be about 1,400 pascals. So we can see it's about 14, it's right about there. All right, so that looks like about 55% of the way up. And initially, just to show everything, initially we had 26, and we were at, what would we say? We were at 1,700. So it's sort of like here or so. Okay, so there was A, my partial pressure at A beginning, and my partial pressure of water vapor at D at the end. Again, we can define the relative humidity either using the ratio of the vapor pressure to the saturation vapor pressure on this diagram, or we can define it on the basis of the specific humidity relative to the saturation specific humidity on this diagram. It's the same exact concept. And that's how you solve this practice problem.